Okay, and if you're not sure why this is so much fun, I'll tell you a little story here that's going to make you understand why this is super cool. So we talked a little bit about, the other day we were talking about Sims. We talked a little bit about how math is abstract and unreal. Did we talk about that? Okay. Like with lines or not, don't exist, things like that, right? Okay, so none of this stuff is real at all, right? Just to quickly rehearse what we talked about. None of this stuff is real. It's all complete, even numbers. It's all made up. Even numbers is just totally constructed, right? So math, none of it exists. Completely abstract, completely made up, and yet it has evolved independently in other parts of our world to be the same thing. And scientists will go one step better than that. They'll say that if you were to go to any civilization in our universe, they would necessarily come up with the same mathematics. Now they might have different symbols, different language, but but fundamentally the concepts are going to be identical. There's nothing else, right? So it's discovered. It's not. That was our discussion, right? It's discovered. It's not invented. Even if you were to go to a different universe with a different number of dimensions, for example, they would still, the beings, biological beings, would still come up with the same mathematics. Now, they would probably leverage different parts of that mathematics to explain their bizarre universe, but it's all part of the same body of mathematics. I mean, we have mathematics that easily explains what the interplay between, say, 4 or 5 different dimensions, right? So we can explain it. It just doesn't have a physical manifestation in our universe, but it would in maybe their universe, right? Same mathematics, though. So by learning math, you are learning a language that is not, it's a transcendental thing. It's not just, like people say English is a universal language. Well, no, it's not. I mean, but math really is. Math is a super universal language because it would actually apply, people really think, in every conceivable universe. So you're learning something that's so fundamental that it's, it transcends everything else, right? So in a way, it's the purest, most pristine thing you could do is to talk about math because it's an entity that lives completely internally in your head. It lives nowhere else. But everybody understands it the same way, right? Bizarre, right? Okay, so, if that doesn't pump you up to learn some math, I don't know what does. Yeah. All right, so let's talk a little about this math stuff here. So we want to try to find a way to resolve this indeterminacy, right? So here's a way we could go about doing this. It's really interesting. I'm going to see if I can think my way through this here. So let's take a unit circle. Okay, let's take a unit circle and let's draw some different shapes in this unit circle. Okay, let's look at, for example, let's look at, I need to put lines into. There's a blue triangle, right? Defines some angle theta. Oops. We'll look at a red sector. those perfectly. There we go. And let's look at a green, another green triangle. Now assume that those lines are all overlapping, right? You get that? Okay, does that make sense? So the green and the blue are they're supposed to overlap. I just want you to be able to see all three of those. Okay, which of those shapes has the biggest area? Blue. Second biggest area. Third. Green. Okay. All right, so this is a unit circle. So let's come up with the areas of all three of those. That's a bad color, blue. I'll use this color, blue, instead to kind of calculate areas here. So what can you tell me about the blue triangle if it's a unit circle? And by the way, these are also intended to be, this is a right triangle. I guess I should have that, shouldn't I? So it's a right triangle. Okay, makes sense. The blue. Say it again. Bottom, the base is 1. Good. Okay, so the base of the blue triangle is 1. That's good. If this is theta, then what would the height be? Anybody know? Let's call the height, we'll call it blue y for a second. Let's solve for blue y. How are we going to do that? It's a right triangle, so that ought to propel you towards maybe a strategy. What do you think? Yes, sir.
Sine theta equals y over 1.
Okay, is it right idea of a tangent theta, right? Tangent's opposite over adjacent. So we could say tangent theta equals y over 1. So then what is y equal to? Tangent theta, yeah. Okay, so we could go ahead and replace this y with tangent theta, right? That's the height. Okay? But while we're on the subject of triangles, let's do the green triangle. Any part of that green triangle that we know? Okay, the base is 1, true. Anything else? Okay, so this other side is also 1, isn't it? Now that might be more useful. If we want to come up with the area of this thing, what's the definition of the area of a triangle? We all know that. 1/2 base times height. So we really need the height of the triangle, don't we? Right? Okay, so let's drop an altitude down. You guys all know what I mean when I say that, right? So we'll go drop that altitude down. And what can you tell me about the height of the triangle then? Let's call it green y for a second. Can you come up with a relationship, trig relationship for green y? So, okay, so tangent. What do we know here? Now, just for a second, let's look. I know the green triangle represents this whole thing, right? But would you agree that the small right triangle created by the altitude has the same height as the big green triangle? Okay, this is a strategy in math we use a lot. It's a logical strategy, and it's a great one. Physicists use this constantly. If you want to try to solve a problem, a lot of times you might trade it for a different, completely different problem that has the same solution, right? So let's instead focus on just this little right triangle up here. I'm taping this right. Oh yeah. Okay. So what's the height of that one? Is there a trig relationship between y and the other sides of this small green right triangle? There's the theta. What is it? Sine, isn't it? Right? Sine theta equals opposite, which is y, divided by hypotenuse of this little green right triangle. Everybody agree? Which is 1. So what's the height of the green right triangle? Sine theta, which therefore is also the height of the big green triangle. Okay? Okay, so now we've got some important sides in these triangles. Let's establish some areas. So let's do the area of the blue triangle then. I'll just call it blue A. Half the base times the height, right? So that's half times 1 times tangent theta. Just, would you agree, it's just tan theta over 2? Do you agree? Okay. How about the green area? Yeah, that's just going to be half the base, which is 1, times the height, so sine theta over 2. All we need now is the red area. Okay, this is, I would claim, a pretty easy one to figure out. We know that the angle is theta, and this is just like a piece of pizza, right? How are we going to find the area of that one piece of pizza? Maybe you want to, I'm only going to give you one hint. I want you to come up with it. It's a ratio, maybe. Oh, to the circumference? Okay, you're on the right track, aren't you? Yeah, you are. You're right. Okay, I see what you're saying. Theta is a part of the whole circumference, isn't it? Right? Everybody agree? Okay, this is, by the way, why, did you ever wonder, you guys probably talked about this a ton last year in pre-calculus, or the trig part of pre-calculus, right? But what are the two ways that we typically use to measure angles? Degrees and radians. Which one do you like better? Okay, good. Good answer. Do the two, is there a reason we have two different ones? Does it bother you a little bit that degrees, why 360? The answer is kind of just a matter of convenience. Why 360? It's highly divisible. That's it, right? You can divide it by 4 easily. You can divide it by lots of things, right? It's got lots of factors. That's the only reason 360 was chosen. Doesn't that bother you a little bit? That it could be anything? Could have been 3,600 if we wanted to. Could have been 1,000. Could have been anything, right? Why 360? So something's inherently wrong about that. Degrees, using 360 degrees, just, it can't be a fundamental thing, can it? So at some point in calculations, like in physics, we'll run into this, those of you in physics, you can't really mix linear measurements and angular measurements involving degrees, because degrees are made up, just arbitrary. What about radians, though? That must not be made up because it's such a weird number. 2 pi radians for a circle. Why would we choose that? It's inconvenient. Okay, that one we didn't choose. That one was foisted upon us by the math gods. That one is not arbitrary. That one means something. Radians means, if I take a unit circle, here's the easiest way to understand why radians are so good. If I take a unit circle, what's the circumference of the unit circle? 2 pi. Ah, okay. So the distance that an ant walks along the unit circle is just going to be some fraction of 2 pi, isn't it? Right? So do you see that actually radians stand for something? They stand for the arc length described by an angle on the unit circle, right? So they work. If you ever want to mix linear and angular measurements in a way that's fundamental, like we'll do in physics, you got to use radians, because radians mean something, right? That's a fundamental part of the universe, the 2 pi radians. So, okay, so then, where are we going with this? Well, you had a great idea. You said that the circumference would be 2 pi.
The red section, we convert to 2 pi as it is.
Okay, good. So what's the area of the circle? Pi r squared, right? And what's the radius in this case? So what's that work out to be? Pi. Yeah, so the area of the whole circle is pi, isn't it? Right? So wouldn't you agree that the red area to the whole area has to be the same ratio as the red angle to 2 pi? That's kind of where you were going with that, wasn't it? Right? Okay, so then we ought to be able to come up and do a little math here, right? So we can say capital A stands for the red area divided by the area of the whole thing must equal theta divided by the distance around the whole thing, which is 2 pi. Right? So if I solve for A, what do I get? Yeah, theta divided by 2, don't I? Everybody agree? Okay. All right, so we've got these 3 areas. You already told me that these areas are, the blue area is going to be the bigger, regardless of the angle, right? I just drew one representative angle, but regardless of the angle, as long as the angle is between, say, 0 and pi pi halves, right? This relationship is going to be maintained. Agreed? Blue is the biggest, red is the middle, green is the smallest. Okay? So we ought to be able to say then, we could put these in some kind of an order. We could say tangent theta over 2 is greater than theta over 2, and theta over 2 is greater than sine theta over 2, right? Agree? Okay. Well, we have an inequality here. As long as I add or subtract something to each part, I don't flip the signs. As long as I multiply or divide all parts by something positive, right? I don't have to flip the signs. If we're going to constrain this in such a way that we're going to say, let's just say that theta has to be greater than 0 and less than or equal to pi halves. That'll be fine for us to do for the point of our argument. Okay? So then, if I were to multiply each of these by 1 over sine theta, that's a positive number, isn't it? Everybody agree? In our domain? Okay? So I don't have to flip the signs. Well, what's this going to do? If I rewrite this in terms of sine and cosine, what does this one become? Sine theta over 2 cosine theta. Everybody agree then? Right? This guy is just, we already know what he is. He's just theta over 2. And this guy is just, whoops, wrong color. Sine theta over 2. Okay, so if I want to then divide, I'm going to multiply all of these through by, let's go ahead and make it 2 over sine theta. Okay, multiply everything by 2 over sine theta. So what is, if I do that, I'll write that step down. What am I going to get over here? What's this guy going to become? 1 over cosine theta. Okay. What does this guy become? So the 2's would cancel. I'm going to get theta over sine theta. Everybody agree? If I multiply this by 2 over sine theta. Okay, and then this guy is just going to be 1, isn't it? Okay. Okay, good. Now, let's take this. This is such a cool proof. Totally geometrical proof. I love it. Okay. Now let's take the reciprocal. Okay, but what happens if I take the reciprocal? take a numerical example. Let's just take a couple fractions. Say I had something like 1/2. So 1/3 is greater than 1/4 and less than 1/2. If I flip that, what am I going to get? This becomes a 2, that becomes a 3, that becomes a 4. Signs change, don't they? Okay, that's one we don't talk about very much. If you take the reciprocal of an inequality, you flip the direction of the inequality signs, right? So this becomes a cosine theta. This becomes sine theta over theta. And this is just 1, right? But the directions change. Okay, now let's take a limit. Let's take a limit of everything. Let's take a limit as theta approaches 0. Okay? Okay, so we're going to end up getting then, here we're going to get the limit of cosine theta as theta approaches 0, right? Here we're going to get the limit of sine theta over theta as theta approaches 0. Aha! Isn't that what we're gunning for? Right? If we go back a page or two, theta or x doesn't matter. Isn't that what we're trying to find? Right? What that is? Oh, what am I telling? And here we get kind of boring one. We get the limit of 1 as theta approaches 0. Okay, well, what's the answer to that limit? 1. What's the answer to that limit? 1. And what does this have to be then? It has to be 1. It has to be 1 by something called the squeeze theorem. This is a theorem. Let's look at it this way. Same kind of deal. If we've got, what was our biggest blue? So if I've got 3 functions, let's just call this one g of x. Let's call this one f of x. And let's call this one h of x. Okay, here's what the squeeze theorem says. It's in your book. But the squeeze theorem says that if in some interval surrounding a value, call it c. So let's superimpose, I'm kind of using my own words for this. We'll look at the real one in a second. But if we're in some interval surrounding, we'll call it a, surrounding a value a. If in some region surrounding a, g of x, f of x is greater than h of x and less than g of x. Now, over here, they get all mixed up. But if we just take some region of values surrounding A, like, say, this region right here, that's true, isn't it? Everybody agree? Okay, if that is always true, that g of x is greater than f of x is always greater than h of x, then if that's true, and if the limit of, what I call the top one, or g of x, as x approaches a equals L, and the limit of, what's the bottom one, h of x? Limit of h of x as h approaches a equals L. So I guess this is L right here, isn't it? Right? Then what has to be true? The limit of f of x has to be squeezed to L also, doesn't it? Right? right? See why they call it the squeeze theorem. Because the middle function is getting squeezed to the same limit, right? So by the squeeze theorem, what can we say here? Well, we can say by the squeeze theorem then, the limit of sine theta over theta as theta approaches 0 is 1. Got an answer. How about that? That's pretty cool, isn't it? Right? What are we really doing here? You can look geometrically at this and you can say, okay, well, as theta goes to 0, what's happening? Well, these are all converging on the same, right? Okay. Make sense? All right. So we can use that. That was just an opportunity. I don't take a ton of opportunities to do lots of proofs in here. You'll do more proofs in college, but this is a pretty good proof to go through because it's so geometrical, right? So how do we use this thing then? Let's just look at, what did I do there? I don't know. I've done this before, I remember, but I just don't remember how to get out of it. That's the problem. Any ideas? What? Usually there's a little button here I can hit and it comes back. Well, I might have lost that. Put that in. Oh. Oh no, I think I really did lose it this time. Okay. I don't think I saved it though, so I probably lost it. Oh my gosh. Well, it's on video at least. Whoops. So we know what the answer is. Darn it. That's not good. It's on video. So if we've got this limit, how could we do something like this then? What if I wanted you to find the limit, evaluate the limit of, let's say, how about cosine theta over tangent theta as theta approaches 0. If I try to evaluate that directly, what do I get? Actually, maybe that's that one. Let's do this instead. Let's do I don't know. Yeah. Let's do this instead. Yeah, let's make it. Like that. Well, if I try to evaluate directly, what do I get? You get 1, don't you? Or no, you get 0 or 0, right? Okay, and is that equal to 1? You can't say immediately that's equal to 1 because this is different than this, isn't it? Right? Something I would urge you to do. What does it mean when we say sine squared theta? Okay, it's a good, there's some ambiguity there. These are different things, right? Let's just take a second. These mean different things. Sine squared theta and sine theta squared. Very different things. What's the bottom one mean? Sine of, okay, I'm hearing differently. I'm hearing sine of theta times sine of theta. The angle is squared on this one. Right, good. There are implied parentheses here around the theta squared. Okay, what does this mean? Okay, good. That means the quantity sine theta squared, right? At least in your head, you always want to rewrite it that way, right? So then I could rewrite this as what? Sine theta times sine theta. Good. I can rewrite this as the limit of sine theta times sine theta over theta, right? Well, I can divide the whole thing by theta, but isn't that the same thing as just dividing one of those by theta? Right? If I multiply straight across, if that's over an invisible 1 right there, same thing, right? Okay. So technically, I can use my properties of limits here, right? Because if I have a limit of a product, what can I do? This is kind of stuff I just breezed through the other day. I can separate the limits, can't I? Right? So I could rewrite that as the limit of sine theta over theta as theta approaches 0 times the limit of sine theta as theta approaches 0. Okay, what's the answer to that limit? 1. That's our special limit, right? So then this is equal to, yeah, that equals 1 times the limit of sine theta as theta approaches 0. And what's that? 0. So the answer is 0. Okay. What was our goal here? Our strategy. Our strategy was to use. In this case, there wasn't much to do, but I could use trig identities. I could use definitions of compound trig functions to rewrite the original expression in such a way that a sine theta over theta pops out. Because we know the value of that, that's 1, and a lot of times that's what removes the indeterminacy. That's what gives us the 0 on top and the 0 on bottom, right? Make sense? I would argue that there's kind of a shorthand notation here, and you could have just maybe done that. Okay, we know that we can separate those limits. It's just a lot of writing to separate them, right? So we know that they act the same way. I can take this limit independent of this limit and multiply the limits, right? That make sense? Okay. Another one. Let's see. I'll get one out of the book. Okay, that's a good one. What do we want to try to do first? Try to evaluate it, but if I do, what do I get? 0 over 0, yeah. Okay, so work on that while I take a roll. Okay, what do you think? What might we do on this one? It's 0 over 0, right? But that's not one of our special trig limits. We only have one at this point. I'll give you another one here at the end of the period. But what could we do to that? When you see a tangent, good. It's always a good idea when you're trying to simplify these things, if you have a composite trig function, to write it in terms of sines and cosines, right? So we could write that as the limit of sine x over x cosine x as x approaches 0, right? Now, can we split this up in a convenient way? Okay, so we can break this apart into sine x over 1 over x, because that, remember, that's our special trig limit. That's the one that we know, okay? So if we write it as sine x over x, then what are we left with here? Okay, good. And if we take the limit then as x approaches 0, what does this one go to? And this one goes to 1 also, doesn't it? 1 over 1. So the answer is 1. Yeah. Okay, so we can add another trig limit. Let's do that. I'll do it here. Okay, so I better give it to you then. So the other one we get is the limit of 1 minus cosine x over x as x approaches 0 is 0. I'll just give that one to you. That one you don't use as much, honestly. All right. What's that? I've got a little bit due. Is that going to work? Is that going to work? I mean, here's the thing. That's going to be the recommended due date, but I'll leave it open for a while with no penalty. Okay. So if you don't have it done, you can finish it up over. Roundup. I'm kind of going to do that to you guys in calculus. I'm going to give you sort of where I think you ought to be, and I know you're busy, so you're going to try to stick to that schedule, but if it slips every once in a while, I'll give you like another week to turn stuff in.
I'm going to be gone during
Okay.
Can I come in during lunch
And get the homework? Sure, yeah, it'll all be online. Everything will be on the physics module.
And I need a little help with one of the lines for this class.
Okay, yeah. So come in during TA and I'll just request you when you get here.
I'm leaving during.
Oh, I gotcha. Okay.
Can I have a note? I have to go to this.
Yeah, you can. Where are you headed? Oh, that's a long ways away, isn't it?
University Station. Hey, Aaron. Rich will be gone tomorrow. I'll get his stuff on.
Okay, perfect. That works. Uh-huh. There you go. You betcha. Yeah, so when do you want to, let's see, how's that going to work? What do you have fourth period? You be here fourth?
I think,
Any chance you can sneak down for a little bit during fourth? Because they'll be working. Probably not.
I could probably actually. We're doing safety and robotics.
Oh,
So
okay.
You could help me now.
Yeah, gosh, now it's going to be tough. I got to do a bunch of, I got a bunch of things I got to do before fourth. Well, I'll tell you what. Whatever you don't get answered, don't sweat it, because we can do it when we get back from Roundup. It's no big deal.
It was like delta x.
Gotcha. So here's what I'll do then. Tomorrow's going to be kind of a work day. I'll go through one or two of those because I want to before Roundup. I understand why those are a little tricky. I'll tape it. It'll be up there. You can just maybe look at that over Roundup, and if you still have troubles, do your best. If you still have troubles after Roundup, it's no big deal.
Okay, and
Yeah.
I'll be here tomorrow. So.
Oh, you will be here tomorrow? Oh, no problem then. Okay, yeah, we're good.